Let's do further examples of Gaussian elimination. And in the process, I'm going to show you another nice application of Gaussian elimination. And it's that you can use Gaussian elimination to convert equations of lines and planes into parametric form very easily, because Gaussian elimination tells you automatically which variables are free variables and so on. Okay, so consider this problem. Find the parametric equation of the following geometrical entity. So we have this equation, x minus 4 equals y equals z plus 1. So already, if we remember from chapter 1, this is the equation of a line, okay? So if we wanted to find the parametric equation of this line, we would have to find a particular solution to R0. So we would say we would have to find R0 and then a vector parallel to the line B, which we could do, okay? We did problems similar to this. Alternatively, we can interpret this as being two separate equations, right? So basically we have x minus 4 equals y and y equals z plus 1. So those are two different equations. So this is a system of equations where the unknowns are x, y, and z. So why not interpret it in this way? So let's write it in the form we are used to for linear system of equations. This would be x plus minus y plus 0z equals 4, and 0x plus y minus z equals 1. I rewrote it just putting x, y, z on one side and the independent coefficients on the other side. Yes? So this means we have the following augmented matrix: 1, minus 1, 0, 0, 1, minus 1, and the independent coefficients are 4 and 1. And now we can do Gaussian elimination with the good news that this is already in row echelon form. Why? Because row 1, what is the first non-zero number? This one. Row 2, what is the first non-zero number? This one. Are all of the pivots to the right of the pivots above? Yes, they are. This pivot is to the right of this one. Therefore, we can say that this is in row echelon form, and we can solve the system very quickly. Yes? So how do we solve it? Well, there are two pivots, but there are three columns. So there is a column that doesn't have a pivot. And this is the column associated to z. Remember, the first column is associated to x, the second is associated to y, and the third is associated to z. So here we have changed. Normally I used x1, x2, and x3, but the names are irrelevant. We can use x, y, and z. Yeah? So the third column doesn't have a pivot. And therefore, z is a free variable. So z equals lambda. Okay? And now we can solve the other variables by inverse substitution. So row 2 is telling us that y minus z, which is lambda, equals 1. Therefore, y equals 1 plus lambda. And row 1 is telling us that x minus y, which is 1 plus lambda, equals 4. Therefore, x equals 4 plus 1, 5, plus lambda. So x equals 5 plus lambda. So we have solved all the variables x, y, and z, and now we can write it in vector form. So r, which is equal to x, y, and z, is equal to 5 plus lambda, 1 plus lambda, and lambda. Or if we write it keeping the independent terms first, and then plus lambda times 1, 1, 1. Right? And that's it. So this is now our solution R with a free parameter lambda. And this is the equation of a line. This is the parametric equation of the line that we had written here. Yes? So by using Gaussian elimination, we automatically found that z was a free parameter, which was equal to lambda. And this, in a way, this enabled us to calculate R0, which is a point in the line, and V, which is a vector parallel to the line. So we could write the line in the usual notation. Okay? So thank you very much for watching. Well, maybe before that, so remember, we also knew that a line could be written like this. So comparing this with the original equation, we could have found R0 and V, yes? And if you notice, R0 would have been different. So if we had used this trick to find the line, R0 would have been equal to 4, 0, minus 1. While V would have been equal to what is dividing, which is 1, 1, and 1, yeah? So V would be 1, 1, 1. And this is still the equation of the same line. Even though we found a different R0, remember R0 is any point in the line. So the fact that we found a different R0 doesn't mean it's wrong. This is the same line. In fact, you can check that if you add 1 times 1, 1, 1 to this R0, you end up with the R0 that we found using Gaussian elimination. Yeah. So it is still a different point in the line, but it's still a valid point in the line. Let's do another example. Imagine I give you the 3D equation of a plane in 3 dimensions is given by x equals 1 minus y. Okay, so this is the equation of a plane. Find the parametric equation of this plane. So you could either use the trick that nx times x plus ny times y plus nz times z equals a number d to find the normal vector and then find some solution for the plane, so some point for the plane. But this is the methods that we were doing in chapter 1. Or we could do Gaussian elimination. How can we do Gaussian elimination? Well, you can say that this is 1x plus 1y equals 1. It's a single equation with 2 variables, okay? So how stupid would it be to just write it as an augmented matrix? We are told that this is in 3D, okay? So actually we should write plus 0z equals 1. So it's a single equation with 3 variables. So the matrix would be 1, 1, 0 times vector xyz equals vector 1. Yeah, that's the system ax equals b. So the augmented matrix is 1, 1, 0, line 1. So can we do Gaussian elimination? Well, yes, we can blindly follow the rules. It's a bit strange because we only have one row. So by definition, we only have this as the pivot. And this pivot is the first pivot. It's to the right of all the pivots above because there are no pivots above. So it's already in row echelon form, okay? So then we could say that there are 2 free variables. The 2 free variables are the columns without pivot. So y and z must be free variables. So we can say y equals alpha, z equals beta, following Gaussian elimination procedure, yeah? And now we can obtain x using inverse substitution. So we start with the last row, which is row 1, which is saying that x plus y, which is alpha, equals 1. Therefore, we can solve that x equals 1 minus alpha. So we have found all the variables, x, y, and z. If we write it in vector form, x, y, z, we know that x is 1 minus alpha, y is alpha, z is beta. And we can write this, first the independent terms with no alphas and no betas, plus alpha times the coefficients of alpha, plus beta times the coefficients of beta. And like this, we have found the equation of a plane with 2 free parameters, alpha and beta. And therefore, in the process, we have found R0, and we have found 2 vectors that are contained within the plane, right? So it's quite amazing how interpreting this really simple equation as a linear system of equations, and therefore writing the augmented matrix, we can immediately see that y and z must be free variables because they are columns without a pivot. So it's a very nice alternative way of finding the parametric equation of things like planes. Yes. So thank you very much for watching.